Okay. Hello everyone. Hi. So let's start. We'll start the demo class, physical design demo class. So this is the agenda for today's demo. So we'll talk about uh, Takshila VLSI and what are the unique features, and we'll see VLSI semiconductor industry introduction. And after that, what is the eligibility criteria? Okay, what is the eligibility criteria for physical design jobs? And we'll see what are the job opportunities, okay, and industry's salary scope, so how the salary scope and course overview. So what content? So what we'll be learning in the 5 months of course duration. Okay, in training methodology, I will see what are the topics we're going to discuss for 5 months of course duration. Okay, and the planning of the course. Okay, and we'll see technical terms like what is ASIC flow, right? Or it is also called as chip design flow. In that ASIC flow, the main concept of today's presentation is physical design. So we'll see that also. And at last, placement at Takshila. Okay, and what kind of infrastructure and lab facility. And we'll end the session with the question and answers. Okay, so about Takshila VLSI. So one of the premier dedicated institute for VLSI studies. So we offer only VLSI courses. So we are located next to Bagmani World Technology Center, Bengaluru. Uh, faculty and trainers with 15 plus year of experience, minimum 15 plus year of experience, and faculty members who are uh, working in top companies. So will be the faculty members. Okay, and who have proven track record of placement. So many of our students, trainees got placed in uh, MNC companies and good core companies. Okay, so these are the unique features of Takshila VLSI. 100% placement assistance from our side. Okay, so maximum will push to get placed in any one of the company. Either it can be a service based company or core based company of any. Okay, and industry standard course curriculum, like what industry wants, what is expecting from you. Okay, so that will be a course curriculum. 24/7 lab support. So we'll be giving 24/7 lab support for you. So all the tools, necessary tools will provide, and low cost and value for the money. Okay, let's see semiconductor industry, types of semiconductor industry. Okay, first is product based company, service based company, and EDA. So what is this product based? So product based companies, they have their own design. They have their own setup for manufacturing the products like processors. Okay, and everything regarding the manufacturing unit. Okay, so they have own design. Okay, and the manufacturing unit. But in case of service based company, so that this service based company, they doesn't have any manufacturing unit. Whatever the work assigned by the product base, okay, are they serves as they give some services to the product based company. That's it. Okay. So EDA companies like Cadence, Mentor Graphics, and Synopsys. So these are the tool providers. So mainly you will work on these tools, EDA tools. Okay. See, EDA tools, like what are EDA tools, right? So to manufacture or to develop the design, you need some tools, correct? So these tools, Cadence, Mentor Graphics, and Synopsys are the tool providers. So everything, whatever the EDA work you do on on these tools only. So top 20 product-based companies. So this is a list of top 20 product-based companies: Intel, Samsung, TSMC, Qualcomm, Toshiba, Texas Instruments, Hynix, Micron, ST, Broadcom. Okay, you can see that this is a list of top 20 product-based companies and their rankings, headquarters, total number of chips manufactured per year. Okay, and as you are seeing, this is the pie chart. The day by day, the increase or the production of the semiconductor chips are increasing day by day in the world market. Okay, see, as the number of production increases, the demand also increases. Correct? Okay. See, product base. So most prominently in India, in our laptops, like either it can be HP, Lenovo, or whatever. So Intel is a primary 80% of the laptops will be using the Intel, and other processors like AMD processor, other processors. Okay, and most of the mobile phones uses the Qualcomm Snapdragon processor. There are some other mobiles also, like Realme uses the MediaTek. Okay, uh, so it depends on the product. Okay, and it depends upon the application also. Okay, so service based. So these are the established service based companies like Wipro, Infosys, HCL, Arisent or Eltron, L&T Infotech, Synapse Design, Wafer Space, Mirafra Technologies. Okay, so these are the service based companies, and apart from this, more than 200 plus service based companies are present in Hyderabad, Bangalore, Noida, Pune, various India, various cities across India. Okay, so let's see what is the eligibility criteria for physical design jobs. So either BTech with following branches with 60% in academics plus physical design course completion. Okay, or MTech with following specialization with 60% in academics plus any physical design course completion. So either BTech or MTech. So this is a requirement and required courses. You should be holding a degree here of these courses. Okay, any one of EC or triple ENT. Okay. So what are the job opportunities? Okay, once you're done with the course, so these are the job opportunities. Physical design engineer. So these are the roles or the role name of the role. Okay, job role. STA engineer. So ST stands for static timing analysis. So timing analysis engineer, EMIR sign off engineer, electromigration and voltage drop. As we know, V is equals to IR. So voltage drop. DFT engineer, design for testability, methodology and flow engineer. So one who has an idea of complete flow. So he'll become the methodology and flow engineer and physical verification engineer. So once you're done with the physical design course, so these are the job roles you can apply. Okay. So what is the salary scope? So freshers completed any VLSI course, salary range 4 to 5 lakh per annum, experience 2 to 3 years of experience, 6 to 10 lakhs per annum, and 4 to 6, 12 to 18, and 10 plus year, 25 to 35. So typical salary range. So this is the salary range. Let's see what are the course overview. So what we're gonna discuss in the 5 months of our course duration. So these are divided into some modules. So total 13 modules. Okay, in the first module, we'll be discussing basics of Linux and or Unix operating system. Okay, so working knowledge of Unix commands, file handlings, okay, and introduction to tool command language. So Tickle, and we will also learn Perl also. Perl is also a scripting language. Even TCL is also scripting. So we'll see what is Linux, because we will not work on Windows operating system. Okay, we'll work on Linux. So you need to learn Linux commands. Okay. The next module, basics of CMOS. So basics of CMOS. In that, what is PN junction diode? So we'll start from the scratch, like PN junction diode and BJT, MOS, NMOS, PMOS, and CMOS. Okay, basic working of these devices. Third module is digital electronics. Like what is digital, what is analog, what is the difference between analog and digital, and number systems, various number systems and conversions, Boolean algebra, and what are combinational circuits. So what is a combinational circuits, and about half adder, full adder, multiplexer, demultiplexer, encoder, decoder, comparator. We will be learning all this. Okay, and in the sequential, latches, flip-flops, registers, counters, state machines, okay, shift registers. So these are the circuits we're going to discuss in the sequential circuits. Okay, so this is about the digital electronics. Next, fourth module is about ASIC, ASIC design. So ASIC stands for application specific integrated circuit. So opposite or in contrast with ASIC, we have FPGA. So what is the basic difference between ASIC and FPGA? So ASIC is application oriented, but FPGA is, it's not like that. Okay, so whatever the board or the FPGA board you have, right? So you can dump the code, okay, in the FPGA, and according to the code, the particular FPGA board will work. But ASIC, so ASIC is completely application. So whatever the application you want, suppose I want to make a processor of a high-speed processor, so which is mostly used in the video games. Okay, and next processor I want to use for any student version or student-based laptops. Okay, so in these student version laptops, the processor what you use, the speed of the processor should be in a moderate speed. Okay, and there are some other devices also you need some less speed. So application specific integrated circuit is kind of, we can customize, we can customize the processor or what kind of application we want. So we'll see that the complete flow. So in the later slides we're going to discuss the complete flow of ASIC in a brief. Okay, so this is about the fourth module, and fifth module is Verilog. So what is a Verilog? Okay, basically it is RTL, register transfer level, and what are the concepts. So basic concepts, so how to write, or the basic syntax of the body of the program, and there are different levels of abstractions like gate level, data flow, behavioral, and switch level. Okay, and we'll also discuss tasks and functions also in the Verilog. So at the end of the Verilog module, you will be able to analyze and you can write the Verilog programming. So next is DFT, design for testability. We'll see what are the DFT basics and what is fault modeling techniques, and logic and fault simulation, what is CAD design. Okay, and we'll also see built-in self-test. So DFT is again it's kind of a testing design for testing. Okay, so these are the things in the DFT module. Next is the synthesis. So see, Verilog, DFT, synthesis. So all these are a part of ASIC flow. Okay, so next slides you'll be able to find out what is ASIC flow completely. Okay, next synthesis. So why synthesis is done, and what are the input files required, and what are the output files we'll be getting. Okay, and what are the constraints. So constraints, and what are the optimization technique, what is a wire load model. Okay, basically why we need to do the synthesis. This module explains about complete synthesis. So next, the main part is static timing analysis, part 1 and part 2. So this is very, very important. As a physical design engineer, you should know timing analysis. Okay, so timing analysis. See, I'll give you one good example. What is timing analysis? Suppose if you're traveling from one point to another point, okay, so from A point to B point. So how much time it is taking to reach at B from A? Suppose half an hour, 30 minutes. So similarly, if you're sending a signal Okay, if the signal is uh, if you are sending a signal from one logic to another logic through some combinational delay or through some wires, okay, metal layers. So how much time it is taking? So that is a general layman explanation of what is static timing analysis. Okay, so in this way we'll analyze the timing analysis, the complete chip. So what are the things we're going to discuss in the STA part 1? So understanding of the transition. So what is a transition? What is capacitance, leakage power, internal power, on chip variation. Okay, and different library modeling techniques like NLDM, CCS, ECSM. Okay, so what are these library files or the what are these library modeling techniques? See, in your design you will be having some standard cells and macros or the logic cells. Fine. So for that particular logic cells, there should be some delay. So in .lib file, in library file, all the delay values are mentioned in the .lib file. So that standard cell or the macro needs some modeling technique to define the how much the delay is. So basically, delay is nothing but delay depends upon input transition and the output load. The basic definition of delay is delay depends upon input transition and output load. So the output load values or the input transition values are present in the lib file based on the different library modelings like NLDM, CCS, and ECSM. Okay. Next, timing concepts like setup time, hold time, recovery, and removal. Okay, and pulse width checks and clock gating checks. So these are the concepts. Next, part 2, what is PLL? Because PLL is phasor local loop, so output of PLL is nothing but your clock. Okay, and IO budgeting, input and output port budgeting. So why we need to take care of much with this IO budgeting? Because in a full chip, okay, inside the full chip you will be having n number of blocks, subsystems. So how much time is allocated to for a particular block is nothing but the IO budgeting. So this is completely handled by the top level guy. Okay, and introduction to ECO. What is engineering change order? So these are the concepts we'll be discussing in part 2. Okay, next module, physical design module. In that, what are the input files? What are the sanity checks? So once we load the design, we need to do some sanity checks. Fine. Next, IO placement, input and output port placement. After that, the flow, complete flow in the physical design like floor planning, power planning, placement, CTS, and routing. Okay, so this is the flow like floor planning, power planning, placement, CTS, routing. Okay. Next, physical design. So once you're done the physical design, so we need to do the verification for that. So verification, so in that, design rule checks, DRC rules, LVS, electrical rule checks, and eye drop analysis. So these are the checks necessarily we need to do in the physical verification. Next module, like project execution. So we'll be discussing on 2 projects. Okay. So after discussing the concepts, we're going to discuss the hands-on experience. Next, last module, mock interviews and personality improvement. So we'll make you to prepare for interviews, one-on-one interviews and written tests. Okay, so total hours are, teaching hours are 138 and lab hours are 180 hours. Okay, so you can see here, lab hours are more, right? 180. So you'll be doing more on the hands-on experience rather than theory classes. So training methodology, course duration is of 5 months, daily 1 hour class and lab practice sessions. Okay, so we also provide weekend batches also. Okay, number of students for one batch 15 to 30. So we'll be providing 24/7 lab support. You will be giving the login ID and password, and will provide the material, okay, and will deliver the material to your home address. Okay, so 100% placement assistance, as I already told, and experience the people who are working in the uh, industry, so will be your faculty members. Okay, guys, any doubts? If you have any doubts, please let me know. Okay, so we'll see what is ASIC here. As I already discussed, application like ASIC is application specific integrated circuit. So this is a complete flow. So starting from the specifications, architecture design, RTL and RTL verification, so on till complete chip. Okay, so what are the specifications? So first of all, if you want to start any chip manufacturing or designing of a chip, you need some specifications. So what kind of specifications? So specifications like area, how much should be the area of a chip, clock, okay, how many clocks are frequency, right? And how many input and output ports, what kind of logic modules, whether it is analog module or digital module, okay, and what is the technology node, whether it is like 10 nanometer, 7 nanometer, 5 nanometer chip, okay, and what is the purpose of this particular chip, whether it is used for any high speed application, okay, or any ultra high speed application, okay. So all these comes under the specifications, fine. So these specifications are written, okay, so that we call it as a specification file, okay. So that file, okay, the written file or the complete specification, necessary specifications are given to the architecture design. So architecture team will come up with some architecture. So that architecture shows the blueprint of the chip. So where a particular module should be present and how many input and output ports and where it should be placed. Not what are the connections, bus, registers, flags, everything. So everything, it's kind of a architecture. So architecture is nothing but the blueprint of the chip. So internal modules, where it should be placed. So for that internal module, each and every module, like analog module or digital module or registers, buses, flags. Okay. So for that module, the RTL code is written. So what is RTL here? Register transfer level. So now your blocks are converted into the code form in the RTL. So the user can write in Verilog or VST. Okay. Okay. So RTL. Next is RTL verification. So RTL verification, once the code is written, that need to be verified. Okay. So how we need to verify? How can we verify this? So by writing some test benches, so we'll provide the input test vectors to the test bench. So whether the output is matched, then it is good to go. We can proceed the next stage, that is synthesis. Or else again we need to send the errors to the RTL design. Okay. Next is the synthesis. So synthesis is a stage where you convert the .v file into synthesized gate level netlist file. So again, synthesis contains three steps. First is generic synthesis. Okay, generic stage. Next is mapping, and third is the optimization. So output of your synthesis will be the synthesized gate level netlist. The only difference between before the synthesis and after the synthesis is after the synthesis you will be getting the technology defined .v file, means technology dependent. Before the synthesis, you cannot mention or you cannot say what kind of technology, whether it is 5 nanometer, 3 nanometer, or 7 nanometer. But after the synthesis, the .v, whatever you will be getting, right? That that is the technology dependent file. So once your synthesis is done, next is DFT, design for testability. So in this, we'll be testing the chip. So what are the things we'll do in the DFT means? First, we'll insert one logic, the scan flop. Fine. So scan flop. So you can run the complete chip in two modes. One is test mode, and next is the capture. Okay. So what is this test mode? So test mode is nothing but you are testing the chip. Okay. Next is the functional mode. Okay. Sorry, functional mode. Okay. The basic function of your chip. Okay. And also you can do the bridging faults. Okay. Stuck at faults and stuck at zero faults, stuck at one faults. So many things are there in the DFT. Once here, if it is done, then fine. So we can go to the floor plan, placement, CTS, routing, and sign off. See, from specifications till the DFT, so all these are the front end. Okay, so we'll call it as a front end. From floor plan, placement, CTS, routing, sign off. These are all the back end work. Okay, so we'll see each and every step in backend, that is floor plan, placement, CTS, routing, sign off in the later slides. So as you know, fabrication is nothing but manufacturing the chip. Fabrication, there are some fabrication steps involved. Fabrication, then packaging, testing. Next, ready with the chip. So after this, so chips are readily available in the market. So this is a brief explanation of ASIC flow, or it is also called as chip design flow. So this is a elaboration of the physical design flow, the complete physical design flow. So as I said, floor plan, placement, CTS, signal routing, and timing closure. So timing closure is nothing but for doing the static timing analysis. The next slide we'll see complete physical design flow. So before starting the physical design flow, so you need to know the input files required to start the physical design flow. The first file is gate level netlist file or .v. So this file we'll be getting from the synthesis people. So it is a technology dependent. Next is constraints file, SDC file, synopsis design constraints. So in this file, it contains all the clock information, how many number of clocks and how much is the clock period required. Okay, so basically SDC contains all the clock information. Next is logical library, extension is .lib file. So in this file, your complete delays, the cell delays are mentioned in the form of input transition and output load. Okay, all the cell delay information. Next is physical library, extension is left file. Layout exchange format. This file, whatever the cell libraries which are present, okay, either it can be a macro or standard cell, those cells area information, how much should be the height and width, okay, how many pins are associated, all these physical information of a particular standard cell and macro are present in the left file. Next is multi-voltage domain file or UPF file, unified power format. So this file contains the complete voltage domain information. So suppose if you are working on a single voltage domain, then no need of UPF file. But if you are working on multiple voltage domain file, you need to load the UPF file, because this file contains the multi-voltage or the multiple domain information, voltage domain information. So these are the necessary files. There are some other files also, but we will discuss only this. Okay, there are another files also, but as for us now, so these are enough. Once you do the real time, then you will get to know, okay, so these are the complete list of the input files. The first stage in the physical design flow is the floor planning. So this, whatever you are seeing, right? So this is nothing but one block, the complete block. So before that, I'll show you the tool, how the tool looks like. Then we'll get to know, okay, so what is floor plan and what is placement and all. So this is a tool. Okay, IC compiler, Synopsys IC compiler. So VNC viewer. Okay, so I have loaded all the input files and I also done the floor planning also. So in the floor planning, we'll be doing or deciding what is the height of a standard cell. Okay, so what is the height of a what is the height of the core? Sorry, what is the height of a core and width of the core? So we'll decide the shape indirectly, the shape. So this is the height, right? Correct. So this is the height of your block and width of your block. Once you give this, you'll be get to know what is the shape of your block. Okay, and we'll also give how much. We'll also place the ports also. These are nothing but the ports. As you can see here, if I click on this, then the down description you can see port PCB out to direction is out. So to which layer it is also to which layer it is connected? M3 layer, metal 3 layer. So complete around all the sides of your block, all the ports are placed. Either it can be input and output port. So we have seen input port, we have seen output port, right? So now we'll see the input port. So here you can see, so there is one input port. So direction is in. So to which layer? M2. So floor plan, in the floor plan, we'll decide height and width. We'll place this ports also. So after that, macro placement. So what is a macro? So as you can see here, these are all the macros. Okay. So if I click on this, down you can see the cell or the reference name and how many pins are associated. 153 pins. So first of all, I'll tell you what is a macro. So macro is nothing but a memory element. So inside the macro, there are n number of standard cells. Okay, which contains n number of standard cells. So basically, macro is nothing but a memory element. Okay, so all these are macros. So basic learning of the floor planning is we need to know what are the guidelines to place the macros. So major part of the floor plan is placing the macros. So how to place the macro in such a way that in later stage it should not affect congestion and timing analysis. So we have to keep these two parameters, congestion and timing analysis, while placing the macro. Okay. So I'll discuss few guidelines. So first guidelines is all the macros should be placed near to your IO ports because these macro needs huge power. Okay, so these are called as power hungry cells. All these are power hungry cells because suppose if I place this particular macro here in between, okay, what happens from IO port to this? It requires a lot of power. Okay, the length of the metal layer will be more. Okay, and there will be voltage drop. To avoid this, it is the best practice is if you place this macro near to the core area, okay, or the IO port, then this is fine. Okay, and it is not necessary that all the macros should be placed near to the IO port. Okay, so it's again depends on design to design. So there will be some case that this particular macro are not connected to the IO port. So this particular macro are connected to all the standard cells. So in this scenario, we can place the macros in the center of your block. or the center of the core area. So we have two, one is core area and next is the die, the complete die. The outer boundary, which includes both the core area and the IO port spacing area, which is nothing but the die. So die are the block, both are same. The core area in the core area is nothing but where you place all your macros and the standards. So first guideline is mostly we'll place the macros near to the IO port. Okay. And next is we need to provide some channel spacing between one macro to another macro. As you can see here, if I zoom in, so there is a good amount of channel spacing or the spacing from this macro to this macro. Correct. So there is some spacing between this macro to this macro. So we need to provide some channel spacing. So why we need to place channel spacing? Because each and every macro will be having some pins associated to it. Okay, even this macro contains some pins, and this macro contains some pins, and this macro contains some pins. What happens if I don't provide any channel spacing? Then this macro will be aborted. So the pins associated to this macro are not available for the routing resources, and this congestion is formed. So to avoid this, we need to provide some channel spacing. Okay, next is assigning the fly lines. So what are these fly lines? What are these fly lines? Suppose if I select this particular macro, it shows the connectivity, the virtual connectivity. Okay, so if I select this particular macro, it shows the connectivity to various macros and the various standard cells and various IO port also. The white color lines, whatever you are seeing, right? These are virtual connections. Okay, so based on these virtual connections, so virtual connections are nothing but in later stages there will be some metal layers associated with this. Okay, or the metal layers. Okay, these virtual connections are nothing but the metal connections indirectly. Okay, so this is one of the macro guideline, flight lines, assigning the flight lines. Okay, then after that we'll assign we'll do the we'll do the power grid or power planning. So what is the power planning? Power planning is nothing but giving this complete, one second. Yeah. So power planning is nothing but your complete chip or the block need to be power meshed. Fine. So giving the VDD and VSS rings, stripes, and rails. Okay. Your complete block is connected to a power source, right? Power planning. Without the power planning or without the assigning the power stripes or rails or rings, okay, rings and stripes and rails, the design won't work. Okay, because power is necessary, right? So power planning is nothing but giving the rings, rails, and the stripes. So once you are done, then you can good to go for placement stage. So placement stage, all the necessary standard cells, all the standard cells. As you can see here, so this is the floor plan stage. So all the standard cells are sitting outside the floor plan stage. Okay, outside the core area. Sorry. Okay, outside the core area. So these are all standard cells. Correct. So in the placement stage, all the standard cells should place in the core area. So this is the center of the core area. Okay. So what are the goals of the placement stage? What are the goals of the placement stage? First goal is no congestion. Okay. So what happens if all the standard cells are placed in one location? So thus creates a congestion, correct? And no overlapping. So on one standard cell, another standard cell should not overlap. As I already discussed in the placement of the macro, what happens if macro overlaps? Then pin accessibility will be less. In case of standard cells, also the same. And achieving the good timing values. Okay, so after each and every step, after placement, after CTS, and after routing, we'll be doing some static timing analysis or the timing analysis. So we need to achieve good timing analysis. If we achieve, then good to go. We can do this CTS stage. If not, again we need to fix. We need to fix some violations. Again, we can go for the CTS stage. So basically, placement is nothing but giving exact locations in the core area to all the standard cells. Okay. So basically, your block will look like this. So outer boundary is your die boundary, inner boundary is core, and IO ports, all the IO ports, macros, and the standard cells. Next, once you place the standard cell, next is clock tree synthesis. So clock tree synthesis is, in your block, there will be some sequential elements also. So what is the common input of all the sequential elements? Clock. Without the clock, sequential element will not work because clock is the driver for all the sequential elements. And it is a common input for sequential elements. So clock is associated to one of the port, and from that port, clock is given to all the clock pins of the sequential elements. As you can see, clock is given to one of the port and it is distributed, okay, in a form of a tree. Okay, and it is connected to all the sync pins of your sequential elements. So this clock tree, or forming the clock tree, it is in the form of a structured one. It is not like that randomly will not give any kind of tree structure. So according to the design, according to the size and shape, and how many sequential elements are there. Okay, so we'll take care of all these things. And suppose if there is a long net is there, so we'll place some buffers also, clock buffers in this particular net. Suppose there is one block which is sitting very far from the source. So without placing the buffers, if you give the clock tree structure, okay, or the clock tree, then there will be signal loss due to the voltage drop. Okay, so it is necessary that we need to place some repeaters in the clock path, such that the whatever the clock which are giving at this point is reached at the sync pin of the sequential element. So this is nothing but the synthesizing or the clock tree. So complete giving the clock tree structure and balancing the complete tree, which is nothing but the clock tree synthesis. So once you are done, once your clock tree is built, then routing. The routing involves in the 4 stages. Okay, basically 4 stages. One is the global tracks, assigning the global tracks and track assignment. Next is the detailed routing, and next is we'll fix the DRCs. So first we'll see what is a global. So global tracks assigning is, it is kind of a imaginary routing. Okay, so all the block where the global routes or the tracks are placed, and the complete track assignment is done. So this is nothing but like it's kind of a logical routing. Now it will be converted into the physical routing. Okay, like assigning the actual metal layers are done in the detailed routing. So assigning the actual metal layers. Okay, so see, routing, it can be from standard cell to standard cell, or it can be from standard cell to IO port, and macro to macro routing, or any other. It can be anything. Okay, all comes in the routing, assigning a layers, physical layers. Next is DRCs. So what are these DRCs? These are design rule checks. I'll tell you one rule. There are n number of rules in the DRCs. So these DRCs are given by the foundry or the manufacturing unit. So one rule is we should maintain some spacing from between one metal layer to another metal layer. Suppose this is metal layer 1 and metal layer 2. Okay, and there should be some minimum spacing between this metal layer to this metal layer. Okay, so this is one of the rule, like DRC rule. There are many rules like poly to metal layer. Okay, via enclosure layer. Right? So many rules are there. So this is the end of your physical design flow or the PNR flow. So after this, physical verification. So we need to do some checks like power estimation, ion drop analysis, power EM, signal EM, and physical verification. So in that physical verification, LVS, DRC, and again we'll do the DRC one more time, and antenna checks and any crosstalk noises are present in your design. So if these are done, then we can go for the successful tape out. So this is about all the technical part, that is from specifications till the fabrication and ready with the chip. So now we'll discuss about the placement process. So placement process. So we'll get the clients. So client information. So we have around like 20 to 30 types of the clients or the companies. Okay, so first round of the student, like first round is like collecting all the resumes. Okay, and preparing the resumes if necessary. If we can help how to write a resume and prepare the resumes also. And we'll send the resumes to the client who are hiring, and for them again the shortlisting of the resumes will be done, and for them written test and a series of interview rounds, and final selection of the candidates. Okay, it is not like one or two placement will offer. It is not like that. So till you get placed, uh, we'll be giving the placement assistance. So these are the hiring companies: Intel, Qualcomm, AMD, Sankalp, Siantra, Insemi Technologies, Synopsys, Wipro, AST Global, Sirium, Black Pepper, Synopsys. You can see these are the hiring companies. So these are table of like number of student placed, or the trainees got placed in the Intel. So these are the numbers, like 18 got placed in Intel, 27 Qualcomm, 45 Wipro, Sankalp, 20 UST Global, 16 L&T Infotech, 22 Harrison Electron, 41 Eximus, 23 Minafra, 15. Okay. And list of the students placed. Okay, so the complete detail. So student name and what kind of course, placement company, and location. So each and every detail is available in the the Takshila website. You can, if you want to see, you can go to the placement tab. Okay, you can search in in this website. So these are building Takshila VLSI and infrastructure, lab facility, classroom. Okay. Any questions? So that's all for my side. Thank you guys. Thanks for attending the demo class. So if you have any doubts, please let me know. Okay, thanks one and all. If you have any doubts, you can contact to uh, these contact details. You can call or WhatsApp for admission, and you can do email the below email IDs. Okay, thanks.